Okay, so now what I'm doing is I'm going to be looking at the computation review, and we're going to be basically, most of the stuff that's going to be in the computation part is going to be on Big O. There will be some understanding of time complexity, what things run faster than others, but a lot of it's going to be based upon Big O and Big Theta and Big Omega. So let's first start out with this one's number 12 actually. So give a Big O estimate for each of these functions. For the function g in your estimate, f of x equals O of g of x, use a simple function g of smallest order. So what that's saying is pick the smallest possible one. All right, and so on your exam, what you're going to be asked to do is to pick the one that actually is of smallest order, right? Because you can pick ones of larger order, right? But it's kind of trivial, right? We just want to get the one that's the smallest. So let's take a look at this, and let's start out here. We got n cubed, and what I'm going to do is I'm going to actually distribute. I got n cubed log n plus n cubed plus n squared log n squared, or okay, log n squared, actually log n squared, plus n squared log n plus 17 n cubed log n plus 19 n cubed plus 34 log n plus 38. Now, the thing that you want to get here is that what we can do is we can automatically eliminate any of the polynomials that are less than the n cubed. N, right, the not the constant function, but the linear function, is always going to be greater than log n, right, for n greater than or equal to 1. So consequently, what we'll get is that if we have like an n squared term with even log n squared terms, okay, what that is that's simply just not going to be as big as, say, for example, n cubed log n, okay, and even n cubed at times. All right, but let's just kind of keep that out of there. Let's take a look first at n cubed log n, and I know that's going to be bigger than n cubed because log n, okay, is going to be greater than 1, right? The function. I know also that n cubed log n is going to be bigger than n squared log n. Okay, and so I also can eliminate, there's the 19n cubed, this 34 log n, which doesn't have the n cubed term on it, okay, and the 38, all right? So now all I've got to do is I've got to determine whether or not n squared log n squared, all right, is in fact bigger or smaller than n cubed log n. Well, if you kind of think about it, n cubed log n is equal to n squared times n log n. All right, and if we compare that to n squared log n squared, okay, you can actually cancel out the n squares, and then you're just comparing n log n to log n squared. Well, we know that n log n is going to be bigger than log n squared because n is bigger than log n. So in fact, we can actually factor out one of those log n's, and we get that n is greater than log n. All right, so this function is going to be O of n cubed log n. All right, so what you want to get there, right, we just made some comparisons, right, that log n is going to be greater than 1 in terms of its O. N is greater than log, all right, and then the polynomials just graduate in terms of the bigger and bigger values for the polynomials. All right, now let's take a look at b. 2 to the n, right, and we'll multiply that b times n cubed plus 3 times 2 to the n plus n to the 5th plus 3n squared. Okay? Now if I look at this, I know first I've got that n cubed term, so that's that polynomial, then multiplied by 2 to the n. Well, that's going to be bigger than 3n squared, okay, because n cubed is going to be bigger than 3n squared whenever n is bigger than 3. In addition, we have that 2 to the n cubed is going to be bigger than 3 times 2 to the n because 3 is constant, okay? And n cubed is going to go bigger than 3, so consequently, we're going to be bigger than that 3 times 2 to the n. So now the question is, which one's larger, 2 to the n cubed, right, or n to the 5th? So let's make a comparison. And again, what we can do is we can actually cancel, make this n squared. So is 2 to the n or n squared larger? Well, we've actually seen that 2 to the n is going to be the bigger of the two numbers in terms of the speed, right, for n greater than or equal to, well, let's just use like a 100, right? So 2 to the n is going to be greater than n squared when n gets big, right, or as n goes to infinity. So, right, 2 to the n cubed, right, is going to be greater than or equal to n to the 5th as n gets big. So consequently, what that means is that this function is going to be O of 2 to the n cubed. Our big O, we are going to utilize the value, okay, inside of, not just the polynomial, inside of the function that grows the fastest for our big O. All right, and the rest of the terms basically just go away because as n gets really large, they're basically trivial. Right? We only want to worry about the ones that get really large really fast. All right, let's take a look at number 13 now. So now, find the least integer n such that f of x is O(x to the n) of each of these functions. So now let's take a look at A. F of x is equal to 2x squared plus x cubed log x. And so when I look at that, I've got, I want to pick an n, right? So that's O(x to the n, so that's polynomial powers. So I know that n is going to be greater than 2, right? Because I've got this x cubed term, all right? So n's got to be greater than 2. In fact, n's going to be greater than or equal to 3 because we have x cubed times log x. So again, we want that log x, okay, is greater than, or actually, excuse me, log x is less than x for x greater than or equal to 1, but log x is actually going to be greater than 1, okay, for x essentially like for x greater than e, right? So whatever, 3 really, which is less than 3. So if we pick, say, for example, 3, we know that when x is greater than 3, then we know that log x is going to be greater than 1. So that means that log x, x cubed log x is going to be greater than x cubed when x is greater than 3. So this function f of x is O(x to the 4th, because what we're going to need to do is we're going to need to increase our polynomial by 1. So in this case, n equals 4. What about f of x equals 3x to the 5th plus log x to the 4th? Well, we either x has to equal, or excuse me, n equals 5, or some other number that corresponds to log x to the 4th. Well, but here's the thing. Remember that x is going to be greater than log x, right, when x is greater than 1. So consequently, what I can do is I can actually take both sides to the 4th power. Okay, and since x is a positive integer and log x is a positive integer, okay, this inequality holds. Okay, so x to the 4th is going to be greater than or equal to x to the log x to the 4th, and x to the 5th, right, is greater than x to the 4th, which is greater than log x, or actually greater than or equal to x to the 4th, which is greater than log x for x greater than 1. So that means that f of x is O(x to the 5th. All right, because that is the fastest growing part of the function. O(x). What about c? X to the 4th plus x squared plus 1 over x to the 4th plus 1. Okay, well, if we look at this, let's imagine we're going to take the limit as x goes to 100, or x goes to infinity. So as x gets big, right, of x to the 4th plus x squared plus 1 over x to the 4th plus 1. And so what we know is we know that as x gets really large, what ends up happening is we end up getting that this thing here is going to equal the limit as x approaches infinity, okay, of x to the 4th plus x squared plus 1 over x to the 4th plus 1, and we're going to multiply that by 1 over x to the 4th, and 1 over x to the 4th. Okay? So this ends up equaling 1 plus, and this will be x squared over x to the fourth plus 1 over x to the fourth divided by x to the fourth plus 1. Okay? All right? Which is going to equal essentially, or the limit, excuse me, the limit as x goes to infinity. This, which is essentially going to end up equaling 1. Excuse me, this is going to end up equaling 1. It's going to end up equaling 1. So what I essentially have is I have that this function, as x gets really large, this function is going to go to 1. Okay? Like it's going to end up basically being equal to the constant function 1. So that's interesting. And the reason why it's interesting is because what's going to end up happening is well, simply the question is if this goes to 1 as x gets really large, why not just choose 2? So x to the fourth, all right, plus x squared plus 1 over x to the fourth plus 1 is going to be less than or equal to 2, okay, when x gets big. Well, 2 is a constant function, okay? So, paradoxically, since 2 is a constant function, that means that our function f of x is O of 1, because it's actually going to be less than some other constant function, the constant function 2, as x gets really large. So consequently, that tells me actually that this function, right, is being dominated or governed by this x to the fourth over x to the fourth term, right? It's got a horizontal asymptote. If you kind of remember what that means that, you know, as x gets really large, right, it gets bigger, it's going to get bigger, but then it's going to start coming down, right? And when it starts coming down towards y equals 1, what we're going to get is we're going to get a bounding on that function, right? And so consequently, this function is in fact constant in terms of its big O. Okay, now let's take a look at showing that x to the fourth plus 9x cubed plus 4x plus 7 is ox to the fourth. Okay, so what we're going to do here is we're really going to just look for the witnesses, right? That is the n, right, and the c, such that f of x is less than or equal to c of x squared in this case, because we're looking at x to the fourth, excuse me, c of x to the fourth when c of n to the fourth. So f of n is less than or equal to c times n to the fourth, okay, when n is greater than or equal to what n naught, okay, so some value n naught. All right, so we've just got to figure out what are those two values. So what I want to do is, I already know it's going to be x to the fourth because it's a polynomial, and whenever polynomials are, we were looking at the big O for polynomials, what we're doing is we're saying, okay, well, the highest degree of the polynomial is going to be the dominant one, okay? But we want to show it. We want to pick the right numbers. Well, the first thing I'm going to do is I'm going to compare x to the fourth, okay, to 7. Let's just compare x to the fourth to 7. So x to the fourth is going to be greater than 7 when x is greater than or equal to 2. Okay? So x to the fourth is going to be greater than 7 when x is greater than or equal to 2. Good. So there we are. We're all good. We can actually select a 1 there if we want. Okay? We also know that x to the fourth is going to be greater than 4x when x is also greater than or equal to 2, right? Again, 2 to the fourth, right, equals 16. 4 times 2 equals 8. So there it is. This is proven. Okay? And in fact, we can see that also, another way to do this is to see that x cubed, right, is greater than 4 when x is greater than 2. Then we multiply both sides by x and we get x times x cubed, which equals x to the fourth, is thus going to be greater than 4x. Right? So that's another method that we go about proving something like this or showing something like this. Next up, we're going to go in and we're going to take a look at our 9x cubed term. So 9x cubed, okay, so we're going to say, all right, well, let's take a look, and we're going to have x is greater than 9 when x is greater than 9. I mean, like, that's just how it is. X is greater than 9 when x is greater than or equal to 9. So that means x to the fourth is going to be greater than or equal to 9 when 9x cubed, excuse me, so we multiply both sides by x cubed, when x is greater than 9. So notice that we had x will be greater than 9 when x is greater than or equal to 9. So x to the fourth is going to be greater than or equal to 9x cubed, just by multiplying both sides by x cubed. So we multiply both sides by x cubed. Okay? So now if I look at this, if I look, what's the biggest x value? I have 9, 2, 2. Okay, good. All good. So what I can do is I can just write this and I can say if x is greater than or equal to 9, okay, yep. If x is greater than or equal to 9, then, okay, x to the fourth plus 9x cubed plus 4x plus 7 is going to be less than or equal to, and we can actually look, and since each one's less than, we've got x to the fourth, right, plus x to the fourth plus x to the fourth plus x to the fourth. Because at the point at which x greater than or equal to 9, this is true for every single term, right? We have the x to the fourth, and we're going to add a number that's bigger, x to the fourth, x to the fourth, and x to the fourth. So this is now equal to 4x to the fourth. So if n naught is equal to 9 and c is equal to 4, we have shown that f of x is O of x to the fourth. Another option actually that we have is to replace each one of our x terms with x to the fourth. So for example, if I could change out this x cubed with x to the fourth, and this x with x to the fourth, and the 7 with x to the fourth, right? And so long as, well, actually, in fact, I could just multiply this by x to the fourth. The x to the 0 with x to the fourth. Okay? And so if x is greater than or equal to 1, okay, so the other place here is if x is greater than or equal to 1, then x to the fourth plus 9x cubed plus 4x plus 7 will end up being less than, strictly less than, x to the fourth plus 9x to the fourth plus 4x to the fourth plus 7x to the fourth, which equals, that's 21x to the fourth. All right? And so n equals 1, or excuse me, n naught equals 1. That's the number that we need. And my c is equal to 21. So those are the two different choices that we have for determining our n naught and our c. All right. So basically what we're doing, we're going to essentially just switch out each one of the terms. I mean, probably the easiest way to think about that is to switch out each one of the lower values for x with our highest degree of the polynomial. And then that makes my c, my smallest c, right? And my n naught. It could just stay at 1. Or we can do this kind of argument that we had here, where we select the proper x, okay? And if n naught's bigger than that, if x is going to be greater than 9, right, then we can actually just literally replace it with x to the fourth. So we end up with c equal to 1 and x equal to 9. One of the key things that you want to get here is that the two values, the n naught and the c that we choose for proving that something is O of x whatever, or O of whatever function O of g of x, those values, there's more than one value that'll actually work. Okay? And so what you want to do is you kind of want to understand what's the relationship between the n naught and the c, and how it is that we come about finding them. Okay? What about 4? Determine if the following functions are O of x squared or omega of x squared. So the question is whether or not we could find our witnesses such that we can get something to be O of x, like underneath O of x squared, or totally above omega of x squared. So let's take a look at 17x plus 11. Well, 17x plus 11, okay, is going to be is going to be less than or equal to x squared when x is greater than or equal to 18. All right? So if you kind of think about it, that's exactly what's going to happen. And then you just start multiplying. I mean, it's going to explode. It's going to get big really fast. Okay? So you can actually go check that. We'll check 18 squared. Okay, it's 324. So, and 17 times 18 plus 11. So this part here is 317. So that's 317 is in fact less than 324. Right? And that just proves that that's in fact the case. And as we increase x, we're just going to, get much faster, much bigger, much faster. Okay? Now, what about the omega of x squared? Because that's a little bit trickier. Well, if you think about it, okay, what's going to happen is that the value, we just showed that 17x plus 11 is in fact less than x squared when x is greater than or equal to 18. Well, c has to be greater than or equal to 1. That witness that we need for, let's c of x squared, that value that we need to put in front of c, has to be greater than or equal to 1. So the problem is that there exists a value for x such that when we're past that value, 17x plus 11 is always less than or equal to x squared. So we cannot find a c such that, okay, 17x plus 11 is going to be less than or equal to x squared for x, right, greater than or equal to any n naught, right? Because once we're past 18, 17x plus 11 is always less than or equal to x squared. So 17x plus 11 is not omega of x squared. It's just not. Okay? What about x log x? Okay? Well, let's take a look at this. X log x, all right, well, first, we know that log x is less than x when x is greater than or equal to 1. So what we'll do is we'll just multiply both sides by x. So x log x is going to be less than x squared when x is greater than or equal to 1. So x log x is, in fact, O of x squared. It's important to get that x log x is obviously also O of log x, O of x log x, excuse me, O of x log x. But we are only asking whether or not it's in fact O of x squared. We can figure out a pair of witnesses that gets it always below O of x squared. All right, so consequently it is O of x squared. Kind of trivially, but just like the first one, this was pretty much true all the time. Now, notice, just like in the previous example, x log x is always less than x squared when x is greater than or equal to 1. Okay, so, right, what we get here is x log x will never be greater than x squared. So x log x is not omega of x squared. We need there to be a certain point at which x log x gets bigger than some constant times x squared, and like the other example, it's just never going to happen, right? Because the lowest constant we get times x squared is going to be, well, 1, and x squared is always bigger than x log x. So consequently, that eliminates the possibility that x log x might actually be omega of x squared. Okay. What about x squared plus 1,000? Now, the first thing I want to know is that, yes, in fact, this is omega of x squared and O of x squared. So let's take a look at this. Let's examine it a little further. Okay. X squared plus 1,000, all right, is going to be greater than x squared for x greater than or equal to 1. That's just the truth. So x squared plus 1,000 is omega of x squared. That's actually pretty easy to get. But it's going to end up being omega of x squared. Okay? Now, probably the easiest thing for us to do now is to select and say, okay, well, I'm going to separate. I'm going to take away my 1,000. Okay? So if x, right? And let's in fact see. If x is greater than the square root of 1,000, right, which is equal to, so we want to see, all right, greater than the square root of 1,000, so x should equal 32. So if x is 32, right, so 32 squared ends up equaling 1,024. Okay, so if x equals 32, then x squared, okay, plus x squared is greater than x squared plus 1,000. Right? So if I pick the right x squared, x equal to 32, we now get, right, we're going to get some number that's bigger than 1,024 plus another number that's bigger than 1,024. Okay? Or we just write, if we want to actually just be a little bit more concrete, we could say x squared is greater than 1,000. So x squared plus x squared is going to be greater than x squared plus 1,000, which is our function. So now we made our function, those two things actually kind of equal to each other. And this then gives me that x squared is in fact, so that means that 2x squared is greater than x squared plus 1,000. So if n naught equals 32 and x squared, or excuse me, and c equals 2, we have shown that x squared plus 1,000 is O of x squared, right? We've actually found a constant, 2 in this case, right? Such that when x is bigger than 32, we get 2x squared greater than x squared plus 1,000, right? So it's O of x squared. Now, since x squared plus 1,000 is both omega of x squared and O of x squared, this means x squared plus 1,000 is theta of x squared. It's actually big theta. That is, it is both omega of x squared and O of x squared. So its worst case time complexity is x squared, right? We actually know exactly what we're going to get out of this function, right? When x gets really large, it's basically going to grow like x squared does, like a parabola. All right, now, show that 3x squared plus x plus 1 is theta of x squared. Find the witnesses for both O and omega. Okay, so now we're going to take 3x squared plus x plus 1, all right? And what I'm going to do is I'm going to make some arguments here. All right, first, that x squared is greater than x when x is greater than 1, greater than or equal to 1. Okay, so x squared is greater than or equal to x when x is greater than or equal to 1. And x squared is greater than or equal to 1 when x is greater than or equal to 1. So those things are both true. So 3x squared plus x squared plus x squared. So all I'm doing is I'm replacing now these two values with x squared is going to be greater than or equal to 3x squared plus x plus 1. So now it's bigger than our function. All right. So when x is greater than or equal to 1, okay, and this, by the way, is going to end up equaling 5x squared. 3x squared plus x plus 1 is less than or equal to 5x squared. And so And so 3x squared plus x plus 1, okay, is O of x squared. Now what we're going to do is we're going to prove that it's big omega, or when it is this function omega of x squared. So for omega, we're going to get, right, that 3x squared, okay? I'm going to consider 4x squared, okay? Pardon me. Actually, this is pretty simple. What we'll notice is that 3x squared plus x plus 1 is going to be greater than 3x squared whenever x is greater than or equal to 1, right? And you can just plug in 1 for x. So n naught is going to equal 1, and c will equal 3, as 3x squared plus x plus 1 is greater than or equal to 3 times x squared in absolute value when x is greater than or equal to 1. So x is, or excuse me, so 3x squared plus x plus 1 is big theta of x squared, because it is both omega of x squared and O of x squared. Okay, and in addition to that, we get our witnesses. The first set of witnesses that we have here is for x equal to 1 and c equal to 5. Now there's more than one way to do that, but that's probably the easiest way to think about it. And for our omega, our witnesses are x equal to 1 and c equal to 3. Okay, so this finishes up the computation review. If you have other questions as you're working through the homework, or you have questions about this, please feel free to email me, and I look forward to talking to you soon.